As you gradually draw to the close of the special functions playlist, here we consider modern special functions. So this lesson introduces several major topics in modern special function theory. First of all, we'll look at the Painleve equations, the integrable systems, Q series, basic hypergeometric functions, fractional calculus, random matrix theory. These subjects connect differential equations, mathematical physics, probability theory, number theory, and of course, modern analysis. In fact, I think I'm getting an inspiration from here to do a whole playlist on fractional calculus. Let's see how that goes. So we jump straight to Painleve equations, whose historical motivation we'll see right away. Many differential equations have solutions expressible in terms of classical special functions, such as exponential functions, trigonometric functions, Bessel functions, hypergeometric functions. Around the beginning of the 20th century, mathematicians discovered that nonlinear differential equations whose solutions could not be expressed through previously, they discovered nonlinear differential equations, right, whose solutions could not be expressed through previously known functions. So the requirement was that solutions should have no movable critical singularities other than poles. This property became known as the Painleve property. So the resulting equations define new transcendental functions called the Painleve transcendents. So let's look at the six Painleve equations. So there are six canonical Painleve equations. We have Painleve 1, which is y prime prime equals 6y squared plus x. Then we have Painleve 2, which is y prime prime, which is equal to 2y cubed plus xy plus alpha. And we have Painleve 3, which is y prime prime equals y prime squared over y minus y prime over x plus alpha y squared plus beta over x plus gamma y cubed plus delta over y. There are also Painleve 4, 5, and 6. These equations arise naturally in random matrix theory, statistical mechanics, quantum gravity, Soliton theory, and nonlinear optics. So let's look at an example of Painleve 2. If you consider y prime prime, which is 2y squared plus xy, just like something close to what we have here, 2y cubed plus xy. The only thing we don't have is that alpha, which is more like a constant. So y prime prime equals 2y cubed plus xy with initial conditions y of 0 equals 0 and y prime of 0 equals 1. So if you introduce the fact that y1 is y, right? So if y1 is y, it simply means that if y1 is y, right, and we differentiate y and it becomes y prime, and we say y2 is y prime. If that is then the case, so we make this second order differential equation into two first order differential equations. So that way we can say that y prime, we can say y1 prime is actually y2. And in addition to that, so it means that y prime prime would have to be y2 prime, and that would be equal to, here we have y cubed, that would be 2y1 cube plus xy1. So this converts the second order equation into a first order system suitable for numerical solution. So this one now, we can use things like Runge 4 in MATLAB and, OD integrate, Cyper integrate, for instance, to solve that. And that is exactly what we have demonstrated by this code. So the key thing doing the job here is the solvent that's called IVP, that's the initial value problem, using scipy.integrate. And then we use matplotlib to visualize and numpy for numerical computations. So we defined Painleve 2 with parameters x comma y. So we have y prime, and that's the whole of y. So y is a collection of the y itself and its derivative, and then that returns the derivative of y, then 2y cubed plus xy as given by the expression we have here. So because we have 2y cubed plus xy, so, and with that in place, then the solution will now be we call the function solve underscore IVP for Painleve 2 with initial condition 0, 5, 0, 1. That's x is 0, y is 5. No, or better still, that should be like I think y1, y2. And then we have a dense output, which is true. Then then you have xy 0 to 5, in 500 divisions, and then the solution, you have that. So pick the first solution here. So then you can plot the figure with all this. And then, this is how it looks like. Of course, because I did log, if I remove the log, the nuance is not easy. The nuances are not easy to capture that easily. So, and once you feel that there's more you need to learn from a particular plot, so log becomes very easy. So log is more like zooming into what is happening there. So if I comment out this line now and I run it again, you discover that you have this is the kind of thing you have, you know, and if you look at the fact that the power is like 10 raised per 73, that's a lot. So for you to X-ray, to zoom into it, then you can introduce log. And once you introduce log, then you can see that there's more than what you were seeing the other time. So you see the behavior in a different shape. So it's like you are zooming in into the whole thing. Then we have integrable systems. An equation is called integrable. We know we're talking about modern special functions. So we've talked about the Painleve system, and now we're talking about integrable systems. An equation is called integrable if it possesses enough mathematical structure to allow exact solution. So we have common characteristics, including, first of all, infinite conservation laws. Then you have soliton solutions. You have Lax-pair representations. You have inverse scattering transforms. Integrable systems are among the most remarkable nonlinear systems known, because they possess enough mathematical structure to allow exact solution. So we have an example in harmonic oscillators. If you consider x prime prime to be equal to omega squared x equals 0. The solution is simply x equals a cos omega t plus b sine omega t. I mean, that follows from the standard idea of differential equations. And then the conserved energy in that case becomes E, which is equal to half x prime squared plus half omega squared x squared, which remains constant for all time. That's for the harmonic oscillator. Then we have another example in the Cottage-de Vries equation. One of the most important integrable nonlinear partial differential equations is you. I mean, normally you don't expect partial differential equations to have exact solutions, right? And thankfully, but we have this particular one, the Cottage-de Vries equation, which is ut plus 6uu sub x plus uxxx equals 0. So this equation models shallow water waves. So this is partial u partial t plus 6u partial u partial x plus partial cube u partial x cube equals 0. So this equation models shallow water waves. A remarkable exact solution is this soliton. So the solution to this now, the u is u of x comma t, which is c over 2 sec squared, so square root of c over 2 into x minus ct. And it has the following properties. It travels without changing shape, and then it survives collisions. So imagine a wave that is traveling, and upon collision, it doesn't change shape and all that, and it appears unchanged after interaction. So it's like it is unbent, it is on it's unscathed, it is unsinged, no matter what happens. That's the kind of wave we have here. So that's the Cottage de Vries equation. And then we have that here. So, this is described here. That's the solution. It is described here. And by the time we visualize it, we have this thing. It has a kind of peak around here. And, it looks like not that normal distribution kind of thing, but not quite, right? So we have that. Then we have the Lax-pair representation. Many integrable systems possess operators L and P satisfying L sub T is the collection of P and L, where P and L is PL minus LP and is the commutator, right? So the nonlinear differential equation is encoded in this compatibility condition. So we have 21.3, which talks about Q series. A Q series is a power series involving powers of a parameter Q, right? So that's summation from n equals 0 to infinity of a sub n q raised power n, usually with the absolute value of Q less than 1, meaning that Q lies between -1 and 1. So Q series appear throughout number theory, partition theory, modular forms, and combinatorics. And then we have the Q-Pocama symbol. The fundamental object of Q analysis is, a semicolon Q sub n equals the the multiplication, over the from k equals 0 to n equals 1 of 1 minus aq raised to power k. And then the infinite version is the collection of a semicolon q sub infinity, which is multiplication over k equals 0 to infinity from 1 of 1 minus aq raised to power k. That's the Q per comma symbol. And then we also have so here we are talking about Q series, right? Then we have generally we know Q series is a power series involving powers of a parameter Q, right? So those Qs now we can now have them in different systems. Like the ones we've seen the Q per comma symbol, and then now we're talking about Euler's pentagonal number theorem. So for the Euler's pentagonal number theorem, right, one of the most beautiful Q series identities is the product over from n equals 1 to infinity of 1 minus q raised power n, which is equal to summation from k equals minus infinity to infinity of 1 minus 1 raised power k, q raised power k into 3k minus 1, all divided by 2. This identity links infinite products and infinite sums. Okay, so the Euler's pentagonal number theorem links infinite products to infinite sums. So talking about partitioning generating functions now. Right, this partition function P of n, or rather counts the number of ways to write an integer the number of ways to write an integer as a sum of positive integers. So you pick an integer, you want to see different possibilities of writing it as a sum of positive integers. So we are used to writing a number, right, as a product of prime numbers. But the partitioning generating function is telling us how to write an integer as a sum of positive integers. So its generating function is given as summation from n equals 0 to infinity, p of n, q raised power n equals 1 over product the product from n equals 1 to infinity of 1 minus q raised power n. Example, P4 of 5, right? P4 of 5, P of 4 equals 5, rather. That means that the number of ways in which you can write 4, you know, as a positive integer is actually 5. So for instance, you can write 4 as 1 plus 1 plus 1 plus 1. That's one way. Then you can write that 1 plus 1, 2, right? So you can write that 2 plus 1 plus 1. That is number 2. Then you can write that this 2, then 1 plus 1 is also 2. So that's another way. Then you could have done 1 plus 1 plus 1, that is 3, then plus 1 here. And then you can write that as 4. So it means that the partition function P4 is equal to 5. That means you can write 4, the integer 4, as a sum of positive integers in 5 different ways, which have been itemized this way. So here we have something about product float. You have Q val, that's float 0.3. Define the symbolic variables for the Q per symbol. So this one is talking about per symbol right here. So if you run this now, you just get the 0.612 blah 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 for the value. That refers to this per symbol you have up here. So that's 1 minus AQ raised to power K. So you have the Q here, you have A, Q, K, N. So I guess that should have come over there, but it's okay. Then we move on to basic hypergeometric functions. Still talking about modern special functions. Classical hypergeometric functions are generalized by replacing ordinary factorials with Q per symbols. The resulting functions are called basic hypergeometric functions. So the basic hypergeometric series is R sub R phi sub S of A1 to AR, B1 to BS, semicolon Q, comma, Z equals this summation you have right here from n equals 0 to infinity of all of that. And then that takes us to the idea of the Q binomial theorem. So for the Q binomial theorem, one of the central identities is R is 1 and S is 0. Then you have A semicolon dash, or then comma Q, semicolon Q, comma Z. And you have AZ, comma Q sub infinity, Z, AZ semicolon Q sub infinity, Z semicolon Q sub infinity. So this is the Q analog of the ordinary binomial theorem. As the Q analog of the ordinary binomial theorem. And then, we have a kind of computation here, like that. And we get this result for the basic hypergeometric function like that. So, like I said, I've got an inspiration from these modern special functions to maybe look at doing a playlist on fractional calculus, which has been it's been it's been all over the place now for about, I think, for between 5 to 10 years. So it's been really all over the place, talking about fractional calculus. So fractional calculus extends differentiation and integration from integer orders to ordinary, real, or complex orders. Okay, from integer orders to arbitrary real or complex orders, I mean. So instead of dn dxn, we consider the alpha dx alpha, where alpha can be a fraction, which is, it can be a rational fraction, it can be an irrational fraction like pi. So alpha can be half, it can be pi, it can be 0.7, and all of that. So that is a fractional order now, instead of the integer order we've always known. So talking about fractional integral now, of course, when you talk about calculus, you're talking about differentiation and integration, right? So fractional integral, the Riemann-Liouville fractional integral is given as I raised to power alpha, and that's I alpha f of x, which is 1 over gamma alpha. So you see how special functions come into this. 1 over gamma alpha integral from 0 to x of x minus t raised to power a minus alpha f of t dt. Then we have the fractional derivative. So this fractional integral here, and our fractional derivative, the Riemann-Liouville derivative is d alpha f, which is equal to dn dx raised to power n, I raised to power n minus alpha f, where n minus 1 is less than alpha is less than n. That means that you can your we are alpha lies between n minus 1 and n in short. So an example of this would be what we have now. For powers now, you have d alpha x raised to power m. So this is a general formula now. For d alpha x raised to power m, like that is equal to gamma m plus 1 all over gamma m minus alpha plus 1, then x raised to power m minus alpha. So that's how to differentiate in fractional order, basically. So normally in integer order, right, you bring down the power, whatever power you have, you multiply it with a function with the power reduced by 1. But here now, you have gamma of m plus 1 over gamma of m minus alpha plus 1 multiplied by x raised to power m minus alpha. So it's more or less like the same, because now you are reducing the power of x by the order of differentiation. So if you take m to be 2, for instance, that's the power of x, and then alpha to be half. So it means you have that's a fractional derivative. Then d half x squared becomes gamma m plus 1. So m is 2, right? So that's m plus 2 plus 1, that's 3. So that's gamma 3. M minus alpha plus 1. That'll be m 2 minus half, that's 1.5 plus 1, 2.5, which is 5 over 2. And then you have x raised to power m, 2 minus half, 3 over 2. And then if you evaluate that, of course, first of all, we know that gamma of 3 is 2 factorial, which is 2. And then we know that gamma 5 over 2 is 3 over 4 square root of pi. I mean, we've done this a lot under beta function and gamma function, especially gamma function. And then in that case, it means we obtain the half derivative of x squared to be 8 over 3 root pi x raised to power 3 over 2. So this is the half derivative of x squared, basically. Isn't it interesting? And then we can, so we can do that. We have coefficient of gamma 3 over gamma 2.5. So that's the coefficient you get here, which is 1.5045 and all of that. So that's talking about fractional calculus. So if there's fractional calculus, then we can talk about fractional differential equation. So if you consider d sub t alpha y to be minus lambda y, its solution is y of t, which is e sub alpha into minus lambda t alpha, where e sub alpha of z equals summation from n equals 0 to infinity 0 raised to power n over gamma alpha n plus 1. That is called the Mittag-Leffler function. So the Mittag-Leffler function plays a role analogous to the exponential function in ordinary differential equations. So the exponential function e raised to power x, it plays a central role in ordinary differential equations, but in fractional differential equation, you have Mittag-Leffler function playing the same role. So we go on to talk about random matrix theory. Random matrix theory studies matrices whose entries are random variables. The primary goal is understanding the statistical behavior of eigenvalues. And then we have classical ensembles like Gaussian orthogonal ensemble, GOE, for real symmetric matrices. You have Gaussian unitary ensemble, GUE, for complex Hermitian matrices. And you have Gaussian symplectic ensemble, GSE, for quaternionic self-dual matrices. That's talking about random matrix theory right there. And then you have the Wigner's semicircle law. For large random matrices, the eigenvalue density approaches rho of x, which is equal to 1 over 2 pi square root of 4 minus x squared for x less than or equal to 2. That means that x lies between minus 2 and 2. I mean, x ranges from minus 2 to 2. That's more like what we are trying to say. So, and rho of x is 0. Otherwise, if that doesn't happen, then we have rho of x to be 0. If x lies outside of minus 2 and 2, you know. Now we then import numpy and we try to do all that. So we have random matrix eigenvalue distribution here as shown by this code right here. So it's random, right? So that we have an element of randomness in line 6 here, and we'll take n to be 500. So this is what we have here. So you have the eigenvalue. So it is random. So as you run it, it keeps changing shape because we are dealing with random matrix eigenvalue distribution. So keeps changing like that. It keeps changing. So just keep changing. All right, so we have the Tracy-Widom distribution. Okay, so fluctuations of the largest eigenvalue convert to the Tracy-Widom distribution. So as it's fluctuating, it converges to the Tracy-Widom distribution. One of the remarkable discoveries of modern mathematical physics is that the Tracy-Widom distribution can be expressed using solutions of the Painleve 2 equation. This establishes a deep connection between Painleve equations and integrable systems and random matrix theory. So let's give a summary of the connections when we talk about modern special functions, right? So first of all, the subjects covered in this lesson form a hierarchy of ideas. So starting from classical special functions, we move on to hypergeometric functions, and then Q series. Then we talk about basic hypergeometric functions. They're all connected like that. And then you talk about integrable systems, the Painleve equations, and random matrix theory. These topics form a major part of modern mathematical physics, analysis, probability theory, and number theory. So that takes us to the practice problems as usual. The following problems are intended to reinforce the concepts introduced in this lesson. Problems range from computational exercises to theoretical questions. Unless otherwise, they provide complete derivations and justifications. So as usual, I'm going to solve two of these, but let me flash the questions like as much as we can. So you can see the first two here. You want to verify that the function y of x equals 1 over x does not satisfy the Painleve equation. So all you just need to do is y of x is 1 over x. So you need it for y here. So you're going to have 1 over x squared here. Then for y prime prime, so it means you differentiate twice. So if you put everything together, so your y prime prime, get it. Then if you evaluate this 6y squared plus x and they are different, then it means this y of x does not satisfy this basically. Then you have question 2 here for Painleve 2. Then starting from 3 now, I think we can see from 3 to 6. If I squeeze it, we can see 3 to 6. So here you have questions 3 to 6. 3 to 6 there. Then 7 to 12. You can see 7 to 12 like this. Then we have 13 to 17. 13 to 17. So I'll be solving question 16. That's under fractional calculus. I'll be taking care of question 17. So we are using that formula to compute the half derivative of x cubed. We did for x squared the other time. This one was done in the notes. So then we finally have 18 to 20, or let me just show as much as we can show all the way to 20. So I'll be solving question 16 and question 20. So you see 20, let A be 2, 1, 1, 3. Compute its eigenvalues and eigenvectors exactly. Explain why this matrix can be viewed as a simple deterministic analog of a matrix from the Gaussian orthogonal ensemble. So these are the things we're going to be dealing with. So let's go ahead and do that. Problem 16 and 20. So let's start with problem 16. Problem 16. So problem 16 says to the fractional, use the fractional derivative, use the fractional derivative formula, which is d alpha x raised power m, which is gamma m plus 1 all over gamma m minus alpha plus 1 multiplied by x raised power m minus alpha. Use the fractional derivative formula to compute the half derivative of x raised power 3. That's the job we have to deal with. So let's go ahead and do that. Solution. So the formula speaks for itself, right? First, from d half x raised power 3, we have so if you compare this with d alpha x raised power m, right? That means that alpha is half and m is equal to 3. So we have all that sorted. So with that in place, then it means that we have the half x raised power 3 to be equal to gamma, that's gamma m plus 1. M is 3, so that's gamma 3 plus 1 all over, so gamma 3 plus 1 all over gamma m minus alpha plus 1, from here, m minus alpha plus 1, that's 3 minus half plus 1. Then we have x raised power m minus half, that's 3 minus half. So that's what we have to deal with. So that means we have gamma 4 all over gamma, okay, not square root. Square root is different from gamma. So 3 plus 1 is 4. 4 minus half, that's 3 and half. 3 and half is basically 7 over 2. Then we have x raised power 3 minus half, that's 2 and half, which is 5 over 2. That's the power of x there. Okay, so we are set for other things. So this is d half x cubed, right? So gamma 4 is 3 factorial as we know it. And then for gamma 7 over 2, gamma 7 over 2 is basically the same thing as 5 over 2 gamma 5 over 2 multiplied by 3 over 2 gamma 3 over 2 multiplied by 1 over 2 gamma 1 over 2. I mean, we know that much from what we did already before. So, and all of that multiplied by x raised power 5 over 2. So we move on and we have d half x raised power 3 to be, so we can tidy things up now. 3 factorial is 3 times 2 times 1 all over, so coming here now we have 5 times 3, 15. So that's like 15 all over 8. Then square root of, gamma half, we already know that square root of pi. Gamma half is square root of pi from everything we've done before. So x raised power 5 over 2 now. So we can try to tidy things up. So of course, this 8 can go up. 8 can go up. So we have d half x raised power 3. So that'll be 8 times 3 times 2 times 1 all over 15 roots pi. So mind you, this is gamma half. Gamma half is root pi. So the signs look alike, but be careful because this is gamma and that is not the same thing as square roots. Okay, so, and this is x raised by 5 over 2. So now we have 3 here to be 1, 3 here is 5. So that is 8 times 2, 16. So we have 16 over 5 roots pi, 16 over 5 roots pi, x raised by 5 over 2. Well, you can leave it this way if you like, but for me, sometimes I like to rationalize. So I may want to have 16 over 5 roots pi times roots pi over roots pi, then x raised by 5 over 2, so that we finally have the half derivative of x cubed to be 16 roots pi all over 5 pi. Okay, I mean, maybe not having too many pies may be something some people may not like, but I mean, we can also have it like this. So this is good enough as an answer, right? But we could also go this way if it's necessary. So that's the result for problem 16. So the next thing we'll look at is problem 20. So problem 20, so we have an eigenvalue issue there. So problem 20, not 12, problem 20. So problem 20 says, for problem 20, right, if we consider A to be 2, 1, 1, 3, and consider A, if we consider that, right, we seek its eigenvalues and eigenvectors. I mean, we've talked about eigenvalues and eigenvectors under so many playlists like linear algebra, uh, differential equations, and all of that. Eigenvalues and eigenvectors. Okay. Even under matrices, we've talked about this a lot. In fact, it's one of the most talked about ideas on my channel, right? Under different playlists. So let's go ahead and talk about that. So first thing, uh, generally speaking, right, we know that step one is to compute the characteristic polynomial. So we know that the characteristic equation is the determinant of A minus lambda I equals 0. If you like, that's the same thing like determinant of A minus lambda I. I like this representation a whole lot. Equals 0. So thus, we have that the determinant of A is, okay, well, I can go step by step. 2, 1, 1, 3, all right, minus lambda I. Lambda I means lambda times the 2 by 2 unit matrix. That's lambda 0, 0, lambda. And all of that is equal to 0 this way. So that means the determinant of 2 minus lambda, 1, then 1, 3 minus lambda, and that is equal to 0. So if we evaluate the determinant, that means we have 2 minus lambda into 3 minus lambda minus 1 times 1, that's 1, equals 0. If we tidy all that up, that's 2 times 3, 6. So 2 times 3 is 6. 2 times minus lambda, that's minus 2 lambda. Minus lambda times 3, that's minus 3 lambda plus lambda squared minus 1 equals 0. So if we arrange all of that, we have lambda squared minus 5 lambda, 6 minus 1, that's plus 5. Yeah, and that all of that is equal to 0. So with that done, we can say, so this is our characteristic equation now. So to get the lambdas, right, which are the eigenvalues, so using the quadratic formula, okay, I guess I was using green. Oh, okay, I thought I changed that. Using the quadratic formula, okay. So if we use the quadratic formula, we know that lambda there will just be uh plus or minus. Oh no, that'll be minus b. That's minus b. So this is the coefficient of a squared here. That is a, and this is okay. With this everything together, that's b, and the constant is c. Okay, so we have minus b. B is minus 5, so that's minus minus 5 plus or minus square root of b squared. That's minus 5 squared minus 4a. A is 1. C is plus 5, all of that over 2a. That's 2 times 1. So then we have lambda equals 5 plus or minus square root of 5 squared is 25, then minus 20 all over 2. So we are going to have real roots, two different distinct real roots. So that's 5 plus or minus square root of 5 over 2. So that implies that we have lambda 1, which is 5 plus root 5 over 2, and lambda 2 is 5 minus root 5, 5 minus root 5 over 2, like that. So with this now, we need to go ahead and look for eigenvectors. So we first of all start with eigenvector. Let's start with the first one. To find the eigenvector, for lambda 1, which is 5 plus root 5, all over 2. So we need to solve. We solve A minus lambda at 1 I multiplied by V equals 0. So that means that the first row, right? Um, lambda I. So usually that's like the original matrix is 2 and 1, 3. So that's like 2, 1, 1, 3 minus lambda I. Lambda I is 5 plus root 5 all over 2 multiplied by 1, 0, 0, 1, right? Um, all of that multiplied by what you can call V1, V2, which is all equal to 0. So if we tidy this up, right? Okay, this is somewhat. So let's say, so you have 2y, 1, 3, uh, and then that's 5 plus root 5 all over 2, 0, 0, and 5 plus root 5 all over 2, yeah? Okay, this is more like it. So V1, V2, and that is equal to 0. So if we take row 1, right? Okay, we can even still tidy all of that up, right? So that will be 2 minus 5 plus root 5 all over 2. Then 1 minus 0, that's 1 there. Then 1 minus 0, 1 again. Then 3 minus 5 plus root 5 all over 2. Then V1, V2 is equal to 0. Okay. So with that in place now, um, so if we tidy this up, we know how this goes now. That's multiplication. So because we have two rows here, we have to write this one twice. So that is V1, V2, V1, V2. So for V1 now, so V1, we have 2 minus 5 plus root 5 over 2, all of this. Then 1 down here, okay? Then for the other one, we have 1 up here. Then 3 minus 5 plus root 5 all over 2, all over 2. Or then all this is equal to 0, 0, like this. Yeah, that's fine. So for row 1 now, we have okay, we can still tidy things up, right? Let's see what's happening here. So that's like, okay, I guess I want to alternate now. So that's like 2 minus 5 plus root 5 all over 2, all this into V1, all right, plus V2, and then this is V1 plus 3 minus 5 plus root 5 all over 2, all of that V2, okay, and that is equal to 0, 0. So that tells us that, so with this, we can have, the first row gives this. So 2 minus lambda 1. So in short, we then have, we have V1, okay, yeah, we have 2 minus 5 plus root 5 all over 2 all into V1 plus V2 equals 0. So that simply means that yeah, we have this. Then on the other hand, On the other hand, that means V2 is simply equal to V2 is equal to if we transfer it to the other side, that means we have 5 plus root 5 over 2, 5 plus root 5 over 2 minus 2 V1. So that's one expression there. The other expression is that since this is already V2 here, or we can do it in terms of V1. Okay, we have V2 here. So for the other one, right, from this expression, we can then have um V1 V1 is equal to V1 is equal to 3 minus 5 plus root 5 over 2. Okay. Yeah. V1 is okay, 5 plus root 5. 5 plus root 5 over 2 minus 3 V minus 3 V2. So that way we can have that way, we are looking for V1 and V2. So it means that V1 now can be 5 plus root 5 over 2 minus 3. And then we have V2. V2 is 5 plus root 5. 5 plus root 5 over 2 minus 2. So we can tidy this up. So V1 is equal to okay. So this multiplied by this, now that's 5 plus root 5 over 2 squared. Okay. Then this times this now, that's minus 2, 5 plus root 5 over 2. Then this times this, that's minus 3, 5 plus root 5 all over 2. Then lastly, 3 times 2, that's 6. So that V1 now is equal to 5 plus root 5 all over 2 squared. Then this and this are the same. So that's minus 5 into 5 plus root 5 all over 2 plus 6. I feel I might be doing too much, but let's see. So V1 is 5 plus root 5 all over 4. When you square that, this is squared here, minus 5 into 5 plus root 5 all over 2 plus 6. So let's try to tidy this up. This is equal to, so 25 plus 10 root 5 plus 5 all over 4 minus 5 into 5 plus root 5 all over 2 plus 6. So V1 is equal to 25 plus 5, that's 30. 30 plus 10 root 5 all over 4 minus 5 into 5 plus root 5 all over 2 plus 6. So what can we do? So V1 is equal to, I guess we have to break it apart, right? We have to split everything up as much as we can. So this is 30 over 4 plus 10 over 4 plus 10 over 4 root 5 minus 25 over 2 plus 5 root 5 over 2 plus 6. Okay, this should be minus here. Minus because we split this open, that's minus minus. So that V1 is so we can go 15 over 2 here. Here we have 5 over 2 root 5 minus 25 over 2. Then we have 5 root 2 over 5 plus 6. Okay, thankfully, this can cancel out. Okay, so V1 is equal to 15 over 2 minus 25 over 2. Okay, I mean, 6 here is actually 12 over 2. I think that helps. So that's 15 over 2 plus 12 over 2. That's 27 over 2. 27 over 2 minus 25 over 2. That's That's 2 over 2. So 2 over 2, and that is equal to 1. Okay, so V1 is equal to 1. So if V1 is 1, that makes life pretty easy. So we can go back and get V2. So what's V2 from where we are coming from? So this is V2 now. So V2 is 1, right? So V1 is 1. So we recall that V2 is actually V2 is 5 plus root 5 over 2 minus 3. No, 5 plus root 5 over 2 minus 2, V1. 5 plus root 5, 5 plus root 5 over 2 minus 2 multiplied by V1. That's what V2 is. That's what V2 is. Yeah. So V1 is 1 already, so we just fix it up. So therefore, V2 is equal to 5 plus root 5 all over 2 minus 2 V1. V1 is 1. So V2 now is equal to, so V2 is equal to 5 plus root 5 all over 2 minus 2. So we can try to tidy this up also. So V2 now is equal to 5 over 2 plus root 5 over 2. 2 is 4 over 2, right? So that means we have V2 to be 9 over, no, not 9 over 2. That's 1 over 2 plus root 5 over 2. So that means we simply have 1 plus root 5 over 2. So in this case now, we have V1, V2, where V1 is 1 and V2 is 1 plus root 5 over 2. That's the eigenvector for the first one. So we can conclude so the eigenvector for lambda 1, which is 5 plus root 5 over 2, is V1, V2, which is equal to 1, then 1 plus root 5 over 2. That's the eigenvector for that. Well, we are going to follow the same procedure for the other one, so we just go straight and get that. So I can just go ahead and talk about that straight. So let's go ahead. Also, so following the same procedure, the eigenvector, the eigenvector for lambda 2, which is equal to 5 minus root 5 over 2, is actually that will be we can should I call it the omega 1 omega 2 now? So omega 1 omega 2, if you like, and that is equal to 1 then minus root 5 minus 1 over 2. So like that. So if you go through the same procedure like that. Okay, so with that in place, then we can then say that so with all of that in place, we're good to go. So the interpretation will be that the matrix, okay, yeah, the interpretation, okay, let me just talk about the interpretation, right? Interpretation. So first of all, the matrix A equals 2, 1, 1, 3 is real. It is real and symmetric. It is real and symmetric. Okay. It is real and symmetric. And we know that matrices in the Gaussian orthogonal ensemble are also real and symmetric, except their entries are, are real, right? Except their matrix are real. Therefore, this matrix shares the key structural property of GOE matrices, which is the fact that A is equal to A transpose. Consequently, all eigenvalues are real. Eigenvectors corresponding to distinct eigenvalues are orthogonal. Then spectral methods used in random matrix theory apply naturally. Thus, this matrix serves as a simple deterministic example of the type of matrix studied in GOE. GOE meaning the Gaussian orthogonal ensemble. So, thus, this matrix serves as a simple deterministic example of the type of matrix studied in the GOE. So we have the final answers there, right? So final answers, we have the eigenvalues. Eigenvalues are lambda 1, where you have 5 plus root 5 over 2, and lambda 2, that is 5 minus root 5, all over 2. Then we have the eigenvectors. We have the first set. Let's call it the new one, which is 1 plus root 5 over 2, and then the new 2, big V2, which is equal to 1, then minus root 5 minus 1 over 2. So with that, we come to the end of this interesting video talking about modern special functions. So I'm just going to go back and flash the problems once again for you to try your hands on. I have solved 16 and 20. So again, we have the practice problems. Here you can see 1 to 3, 1 to 3. Then from there we see 4 to 7, clearly, 4 to 7. Then you have 8 to 13, showing clearly 8 to 13. Yeah, 8 to 13. We can accommodate 8 to 13. Then 14 to 6, 14 to 18, showing clearly 14 to 18. Then the rest. All right, so thank you for listening. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and do that right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel also by clicking on join. That gives you some special privileges which you find out when you do that. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.